Hello, this is David Birch at Star Path School of Navigation in Seattle with a note, I hope short, on finding your latitude by the North Star Polaris, the height of the North Star. And this is one of the oldest techniques in celestial navigation. In fact, actually probably the oldest. What brings this about is we have a new book out, a relatively new book out, a short book, which is a backup on celestial navigation. It's the bare things you need to know to find your position at sea, and without any training in celestial navigation. So this book sort of promises that. You could just, if you have one of these plastic Mark III sextants, that's about $30, $40, then, and this book, you can just, if you ever need it, just pull it out of the box, never having looked at either one of them before in your life, and then be able to do celestial navigation and find out where you are. So it's mostly about the sun, doing noon sights of the sun for latitude and longitude, and we have custom tables in the book. The book is mostly tables. There's only about 20 pages on how to use that sextant well, teaching you from scratch, and then there's about 10 pages on how to do all this celestial navigation, literally just 10 pages. And the rest of the book are the tables you need. Still a short book. But the latitude by Polaris part is a little bit special because we want this to be perpetual. We want this to be work any time, and the normal procedure for latitude by Polaris takes you have to have an almanac and you have to have a watch. And I'm going to review that very quickly. But here's the point for now. Let me just go here, and this is the program. This is also a remarkable program called Stellarium. I'll put these links in the discussion there. Stellarium, and it's really phenomenal. And here I'm looking at the sky in the night, or just after sunset or something on around San Francisco, and looking north. And this is the North Star right here. And what we're going to do is what happens is the North Star is not right at the pole. It's a little bit off of the pole. So it actually goes around the pole each night. Let me shut that feature off. Maybe turn this. Whoop, that's not the right one. Excuse me. Maybe this one. Yeah. So there's the hub of the sky, and let me zoom in here, and then turn on the clock, and you'll see that this star goes around the hub just like all the other stars do. And so what we will see, I'll show you the principle. The height of this point right here, the hub of the sky, is always equal to your latitude. And if we had a way to measure that, that's all we had to do. But this star right now in the year 2020, that's about 40 minutes, just a hair less than 40 minutes off the pole. So if we just randomly go out and measure that height, we would get our latitude, but it would be plus or minus 40 minutes. If we happen to, and this, remember, it takes once a day, 24 hours to go around here. If we happen to be out there in twilight and took it when it was right here, when this was around right here, then that height of that star would be our latitude. But if it's here, we're going to have to add 40. Here it's again right or equal our latitude, and then here we have to subtract 40. So that's the process. Now, the Nautical Almanac has a way to do that based on things you look up in the almanac, local hour, angle of Aries, and so forth. And I'll show you that in a moment. But I want to now show that we can do this ourselves in these modern times exactly, well, yes, more or less exactly, like it was done in the 1400s. In the 1400s, they had rules about how you determine what that offset was. Plus or minus, well, in those days it wasn't 40. It was about time of Columbus, it was about 3.5 degrees. So there was a notable correction. And they use, and I'll show you an article. We have a couple articles online now, and this discussion video is sort of a supplement of the 2 articles we have online about this, and the book itself. And I'll show you practice problems and so forth. But we're going to use these 2 constellations over here. This is the Big Dipper, Ursa Major, and then this is Cassiopeia. And in fact, and these things go this way, right? If I turn on the big clock in the sky, these things are going to be going around that way. So that's the way they move. And this is the trailing star. Think of this as a boat going sailing around here. This is a trailing star. And likewise with Cassiopeia, that's an M, right? See, it looks like an M. Now, it looks like, here's the middle, right? I call this a North Star. That's the middle. So Cassiopeia looks like an M from the middle. We're not thinking about the Queen of Ethiopia sprawled out across a throne, the way other people do. We're thinking about it looks like an M from the middle. And so there you go. There's Cassiopeia, like that. And we're going to use the trailing star here. This one is called Sagan, and this one's called Alcade. And these two are going to be our workhorses, and wherever they are in the sky, they're going to tell us how to make the correction to here. And that's called a regiment of the pole. And in the old days, and I'll show you a quick history note we have online about that. This was techniques developed sometime in the early to middle 1400s. And lasted up until, well into the early 1600s, probably even beyond that. Not beyond 1700 much. Okay, so that is that technique. And so let's just real quick, I want to show you what the principles of this, what the principles are. They're stated in this argument, in this book as well, in the articles as well. But let me bring in a reference. I want to bring in our Celestial Navigation book. This is our textbook. I need a picture out of it. Here's the key picture to understanding the theory. In other words, the question is, why is the height of the North Star, the hub of the sky rather, why is the hub of the sky equal to our latitude? Well, if we want to understand that, the first thing we have to understand is that stars are very far away. Very far away, millions of miles. So look at this star. Here's two people on Earth, B and A. Let's say they're 1,000 miles apart, right? 1,000 miles apart. And so A sees the angle of this star at this height, this angle A. B sees it at a smaller angle over here. Now bring the star out another 2,000 miles. Here, see, this is 2,000 miles. Now bring it out to 4,000. Now you see that's still, this guy's always going to get alpha. This guy's going to get beta now, you see. It's a little bit bigger, right? Then go up to this, 3,000. Now 3,000 miles. 3,000 miles. So you see, now look at that angle. This angle that beta sees this star that alpha sees gets closer and closer to the same angle as alpha. The farther you go out, the more parallel that light comes in. And so this is like you see the curvature of the Earth here. Well, that's maybe 2,000 miles on the Earth, 1,000 miles, something like that. This is like 6,000 or 8,000. Now take that out 6 million miles away, and you see, bang, this light from one star is coming from clear, they're all parallel. In fact, it's not just parallel over the surface of the Earth, it's parallel over our entire solar system. So all the light rays from this star Polaris come in parallel across so it's not just across our Earth, but across the entire solar system, so no matter where we are in our orbit. Okay, that's a bit of the background needed there. Now we can go to the article. Let's see where I have that. Is this one the article? Regiment of the North Star. Right, okay. So here now then, this is the end of the theory, then we move on. Here's all these parallel light rays. So here's the North Star, and this is one coming down. So if you're standing at the North Star, that starts right over your head, and it's coming down right through, and it goes right through the center of the Earth. So the geographical position of that star is 90 degrees north. If it were exactly at the hub, 90 degrees north. Now here's another person over here at some latitude, and he sees the star at an angle H. Only this guy sees it overhead. He's at angle H. And now you just look at these two angles and some basic geometry as if you have two angles and one side's perpendicular to the other, and they have mutually perpendicular sides. Like the red is perpendicular to this red, and this blue is perpendicular to this blue. So if two angles are mutually perpendicular, the angle between them is equal. So this H is equal to this latitude. So that's the theory. That's the theory, period. That's all there is to it. So if this star were indeed exactly at 90 degrees, the hub of the Earth, then your latitude, the height of that pole is exactly equal to your latitude. But here's the issue. As noted, that star is not exactly at the pole. back in the day, it was back in the time of Columbus, it was about 3.5 degrees away. And so it goes in a little circle like this. So sometimes you see it high, sometimes you see it low. And so I'm gonna, and then this is getting into the way the early folks correlated where the star was using these two stars here called the guards. And I'm going to, there's a history. We have notes on here about the history of how this technique was originally used, and I'll leave that as some reading if you want to read about the history. And we're going to go to the modern. This is an article about telling time by the stars, because the instrument that they ended up using in historic times was tied to an instrument that was used for several hundred years before Prince Henry for telling time. This is called a nocturnal. And the device that they ended up using in the early days ended up sort of looking like a nocturnal. That's in these articles to read. But here's what I want, a modern regiment of the pole, that's us. And so here's what we're doing. We're using this line between Sagan and Alcade and Sagan, and we're going to measure that. And the actual stars are a little kicked forward here about 15 degrees, something like that, on that line. But that doesn't matter. All we need to do is we need to look at the sky, and we're looking at it as if there's a protractor up there, you see. So here is called Sagan. The angle of Sagan's 90 degrees. Here's Sagan 0. So you just imagine a protractor. In fact, let's see, that's a practice problem. Here we actually, the way you can measure this is you can actually hold up a clear protractor. This is a navigation protractor, Douglas protractor, crystal clear, and you can hold that up and sort of measure those angles. So what we want to do is, like, here's Polaris and here's Sagan right here. And so I want to know that angle, and to me that looks like that's about like here's vertical, and that's about like 20 degrees. And then if I come down here, where is Alcade? See, there's the big cup. There's Alcade, clear down here. So this is Alcade, and this article says, and it's even true to me now as I read it, as I look at it, talking in the microphone here, it looks like this is a little bit bigger. It looks to me like that's like 30. Now these two should be 180 degrees apart, with this one the same as that one. But anyway, so there's just my perception by eye. But then when you put any kind of tool up there, you can start homing in on getting that angle. And usually you'll do it relative to the horizon or relative to the vertical. And that's all we need. We just need to know that angle. And then we have a table set up for those corrections. And then the article also says, and see, here's drawing a line of that, measuring that angle. And here's the corrections. So if the Alcade angle happens to be 200 degrees, then the correction is minus 33, and so forth. So that's the way and then you just apply those corrections. And so that's all you need, this table. And then if you read down here, we tell you how you could actually create that table on your own if you want to. If you forget, you lose your table. But that table's in that book, and that book has all the almanac for the sun, the really nice almanac for the sun. And so it's all in one tidy place. So that's the procedure. Let's see what else we have to show. And then here's a couple examples, and I'll show you some references on that. The pros and cons of this method. Well, the pros are you do it any time and you don't need an almanac, and then there's notes there on how you could maybe do it yourself. The con is that, maybe you can't see one of the stars. And, in fact, we have to admit that the method you do out of the almanac with, using the almanac and a UTC time is going to be more precise. The UTC method with the almanac is going to get you this latitude from Polaris within half a mile or so, if you do it well. Half a mile, at best half a mile. 1 mile would be good. But this method, this backup method that we're doing now, doesn't take a watch, doesn't take an almanac. We're gonna have to call 3 or 4 miles good. But you have to, the whole key is practice. To go out there and practice reading that angle from the sky, and you can practice that sitting on your back porch at night, looking north. So the way you practice is you go out and you look at the sky and you say, you're going to pretend what that angle is. It's just like you practice, I'm going to look at the moon and say, okay, from my knowledge of celestial navigation, what is the true bearing to the moon right now? And I look at the moon and I judge from its phase what bearing it is, for this time of day and so forth. That's good practice, But this is another kind of practice. It's a practice. You look at the sky and you say, what is that angle? Then you come home and you turn on Stellarium. Here's a link to Stellarium right here, this wonderful program, and you just set that up. You come over here. Here's where you set up the latitudes like that. Here's where you set up the times. I'm going to make a video sometime on the use of this Stellarium. It is such a powerhouse. And then you just test to see if you did everything right. Okay, what else do I want to show here? One thing I want to show is, let's see, we've done that. I don't need that anymore. I wanted to show you the traditional method here. The traditional method of doing this this is a page from the Nautical Almanac. And so this is now done in a totally different way. You have a watch and you know the time you took it. And from the time you took it, you look up the GHA of Aries. You subtract your DR longitude and you find the local hour angle of Aries. And then you come down this column. Let's say it was 185. And then you come down here, you get these 3 corrections, A0, A1, A2, right? You get them here. And then what you do is you take the corrected value of the height of Polaris, H0, observed height, and then then they do a trick. They subtract 1 degree, and then that makes all these corrections positive. Recall that the real correction, the real honest correction of Polaris going around that circle is going to be plus sometimes and minus sometimes. So the Nautical Almanac just does a trick. It subtracts 60 minutes so that all the corrections are then positive. That's fine. Okay, then you get the 1, 2, 3 corrections. You add them together and you add them to HO and you get your latitude. Okay, so that's the way it's done in the Almanac. It's perfectly easy. It's just totally different, and you have to have an almanac and an accurate watch. Now, I just make some interesting note. This is, strangely enough, this is the Nautical Almanac. This is the only navigation technique in the Nautical Almanac that's presented in the Nautical Almanac. They don't even tell you how to take a noon sight or anything else. They tell you the background of where all the numbers come from the astronomical data, but they don't tell you any navigation technique except for this latitude by Polaris. So keep in mind there's one navigation lesson buried in that almanac, and that's latitude by Polaris. Okay, so what have we got now? Okay, let me go here to our book. This is the page where it writes about the book, and you could buy the book if you wanted to. In the support page for that, there is a couple things. This book is also used in some courses, celestial navigation courses for the basic celestial navigation. And then here is this is the article we're just looking at. Here's an expanded table. For now, the book the Q tables in the book have bigger steps, because the accuracy is limited. But just to make it a little simpler, here's a download where you can get bigger steps, finer steps on the Q values. The other thing, we put in some extra steps for the refraction correction, how much the light bends. You have to correct your sextant height with that. There's some finer steps here, and again, a few extra steps on the dip correction. The tables in the book are very short because it's really trimmed right down, and so that avoids a little interpolation. And then you've got a couple examples that you can actually practice with. So here's this example 1. Here's the sky. Right there's the sky. Now here's all your data. It's July 19th. That's a UTC is that. DR is that. HS Polaris is that. IC, HC, what's your latitude? Then so that's a practice problem from 2021. So it's kind of looking ahead. And then the solution of that, you can go online and get the solution so you have a practice. And there's another practice problem there. So that is the technique and the procedure. And let's see, mostly very... Yeah, and so that's it. It's a technique. The trick is go out there and practice looking at the sky. You'll be surprised how well you can do that. And then this article here shows some of the techniques. When you're using a ruler or something like that, we found that a piece of tape or something on the bottom makes it a little easier at night to align with the horizon and so forth. So I'll stop there and stand by for questions as they might show up.